All right, let me ask you something. Have you ever had the feeling that you understood something beautifully, right up until the moment you tried to explain it to somebody else? You're sitting there feeling very clever. You've read the chapter, underlined the sentences, copied down the equations, maybe even nodded at all the right places. Then somebody says, "Fine. So what does it mean?" And suddenly the machinery begins to rattle, the gears slip, smoke comes out of the back, and the whole thing collapses in a heap. I like that moment. I really do, because that moment, embarrassing as it is one of the most useful moments in learning. It tells you, very sharply, very honestly, where the real thing ends and where the imitation begins. And nature is like that. Nature is not impressed by how confident you sound. Nature doesn't care whether you can recite the chapter headings. Nature doesn't care whether you've memorized a fancy phrase in Greek, Latin, or Brooklyn English. If you understand something, you can work with it. If you don't, then the first little twist, the first new condition, the first funny-looking example, and bang, the whole thing comes apart. So if you want to learn faster, I'm going to tell you the way I try to do it. Not by magical tricks. Not by superhuman memory. Not by whispering to the universe. No, no. I mean something more reliable than that. I mean by taking an idea, stripping it down, explaining it in simple language, finding the holes, and then going back to repair the holes until the thing actually works. That's all. Simple. Not easy, perhaps, but simple. And the amusing part is, the more honestly you do this, the faster you learn. Not because you're hurrying, but because you stop wasting time on what only looks like knowledge. When I was younger, I noticed something very curious about school. A lot of students could pass examinations on things they didn't really understand. Now that's a marvelous trick if your ambition is to impress an examination paper. But it's a lousy trick if your ambition is to understand the world. A fellow learns a formula. He memorizes the symbols. Maybe he even remembers where the minus sign goes, a tremendous achievement in some courses. Then you ask him a slightly different question. Not a hard one. Just a different one. You tilt the problem a little sideways. And now he's stuck. Why? Because he learned the label, not the mechanism. This happens all the time. You can know the name of a bird in every language on Earth, and when you're finished, you'll know absolutely nothing whatever about the bird. You'll only know something about people's names for the bird. But if you watch the bird, how it pecks, how it flies, how it balances in the wind, how it uses its feet, now you're beginning to learn something real. Learning is like that. You can know the terminology of a subject and still not know the subject. You can memorize an equation and still not know what the equation is saying. You can repeat a definition and still have no feel for the phenomenon behind it. So the first observation is this: the biggest obstacle to learning fast is not ignorance. Ignorance is fine. Ignorance is a clean slate. Ignorance can be fixed. The biggest obstacle is the illusion of knowledge. That's the dangerous thing. Because if I know that I don't understand something, then I can begin working on it. But if I merely feel that I understand it, because the words are familiar and the symbols look friendly, then I won't examine it carefully enough. And then I fool myself. Now I have a very low opinion of methods that help a person fool himself more efficiently. If a method helps me find out where I'm fooling myself, then I'm interested. So here's the central idea. If I want to learn something fast, I try to explain it as plainly as I can, as if I had to make it clear to someone with no special background, maybe a bright freshman, maybe a friend, maybe an empty chair if nobody's around. An empty chair is very good. It doesn't interrupt. Sometimes it also doesn't seem impressed, which is excellent training. Let's go through it carefully. Suppose I want to learn some idea in physics. It could be energy, acceleration, electric fields, probability, whatever you like. The details don't matter at first. What matters is what I do with the idea. I begin by writing the idea at the top of a page. That already helps, because it forces me to be definite. Not all of electricity, not the whole of mechanics, not everything in Chapter 7. No, something concrete. Why does current flow in a circuit? Or, what does acceleration really mean? Or, why does a spinning object resist having its axis changed? One question. One target. Then I explain it in ordinary language. Not fancy language. Not textbook language. Not ceremonial language. Ordinary language. If I say acceleration is the rate of change of velocity, that may be correct, but it might still be empty for me. So I keep going. I say, velocity means both speed and direction. So acceleration can happen if I speed up, slow down, or turn. If I go around a corner at constant speed, I'm still accelerating because the direction changes. Now we're getting somewhere. I can picture it. A car turning. A ball swinging on a string. Something physical. The aim is to translate the symbols into motion, into pictures, into consequences. Because if a formula means anything, it must tell me what would happen in some real or imaginable situation. Otherwise, it's just decoration. Think of it like packing a suitcase. A subject is too big to carry around in its full original form. So you try to compress it. That's what a formula does. It's a marvelous compression device. But if you only memorize the compressed form and you can't unpack it again, then it's useless to you. Imagine someone hands you a suitcase locked shut and says, "Everything you need is in here." Well, maybe. But if you can't open it, what good is that? A formula is like that suitcase. The knowledge is packed inside. If I really understand it, I can open it up and recover the meaning. I can tell you what each part stands for, what changes when one quantity gets bigger, what assumptions are hidden in the derivation, what happens in an extreme case, and where the formula stops being valid. That's understanding. So I explain. And while I explain, something wonderful happens. The weak parts reveal themselves. I notice that I'm using a phrase I don't really understand. I notice I skipped a step. I notice there's a word in my explanation standing exactly where the understanding ought to be. That word is often the camouflage. A student says, "It happens because of inertia." Fine. What does that mean here? Silence. Or he says, "The system seeks equilibrium." All right. How? By what mechanism? What's moving? What forces are acting? What changes with time? You see, the fancy phrase can act like a curtain. Once you pull the curtain aside, sometimes there's nothing behind it except a terrified little guess. Good. Excellent. Now we've found the place to work. That is why this method is so powerful. It turns vagueness into a specific repair job. Now let me tell you the most important part. Most people think the key step is the explanation. It isn't. The key step is what happens when the explanation fails. That's the gold. That's the laboratory. If I explain an idea and I find a gap, I don't treat that as a defeat. I treat it as a discovery. Because now I know exactly what I don't know. That's a tremendous improvement over not knowing what I don't know. So I go back to the book, or the notes, or the derivation, and I look only for the missing piece. Then I return and explain it again. Back and forth. Back and forth. Explain, fail, repair, explain, fail, repair. This is very much like doing experiments. In physics, if your apparatus doesn't work, you don't stand in the laboratory shouting definitions at it. You inspect the setup. You check the wiring. You look for friction, leakage, bad assumptions, hidden effects. Learning is the same kind of business. Imagine I put you in front of a blackboard and say, "Explain why the moon doesn't fall down." Now maybe you say, "Because gravity keeps it in orbit." That sounds nice. But it's only the beginning. How does gravity keep it in orbit? Why doesn't gravity simply pull it straight in? What does in orbit mean mechanically? What would happen if the moon suddenly stopped moving sideways? What would happen if Earth had twice the mass? What if the moon were farther away? Now you begin to see the structure. The moon is falling all the time. But it's falling around the Earth, because its sideways motion carries it forward while gravity bends the path inward. It's a perpetual miss. Now that's something I can work with. I can imagine a cannonball fired faster and faster from a mountain, curving farther and farther until it circles the Earth. That's a picture. That's a mechanism. And then I ask, can I use the same reasoning for satellites? For comets? For planets? If yes, then I probably understand something general. If no, then I've got more work to do. This is how learning gets faster. Not because I avoid mistakes, but because each mistake becomes sharply informative. A vague confusion can waste a whole afternoon. A precise confusion can be fixed in 10 minutes. There's another trick I like. When I'm trying to understand an idea, I test it in 3 kinds of situations. First, a simple case. Second, an extreme case. Third, a real case. Let me show you. Suppose I'm learning about pressure in a fluid. The simple case is water standing still in a tank. The extreme case might be, what happens very deep down? Or what happens if the fluid is almost weightless? The real case might be water flowing through a pipe or air moving over a wing. By walking through those 3 cases, I force the idea to become flexible. It's no longer just something that lives in the exact arrangement shown in the textbook. And that matters, because real understanding has mobility. If your knowledge only works in the example you memorized, then it's trapped there like a bug in amber. Here's another way to think of it. Memorization often means learning the lock. Understanding means learning the key. If I learn only the lock, then I can open one door and no others. But if I learn the key, the underlying principle, then I can open many doors that look different on the surface. That's why I prefer first principles whenever possible. I don't mean I rederive every piece of physics from scratch every morning before breakfast. That would be ridiculous. I'd never get to lunch. What I mean is this: when I'm uncertain, I go downward. I go to the more basic thing. If I'm confused about a formula, I ask what assumptions produced it. If I'm confused about a definition, I ask what observation made the definition useful. If I'm confused about a law, I ask what phenomenon the law summarizes. Downward. Toward the root. Because the root is usually simpler than the branches. That surprises people, but it's often true. The branches are where the subject gets tangled. The root is where the thing begins. A lot of people imagine learning as a kind of smooth accumulation, as if you just pour knowledge into your head 1 cup at a time. I don't think it feels like that at all. To me, real learning feels more like reconstruction. You start with some scattered pieces, a few facts, a diagram, an equation, a vague impression that everybody else understands this better than you do. Then gradually, by playing with it, questioning it, and trying to explain it, the pieces begin to lock together. At first it's awkward. Then it becomes coherent, and when it becomes coherent, it has a certain feel. You can move it around in your mind. You can predict what happens if one part changes. You can recognize when someone says something that sounds nice but can't be right. That's a lovely feeling. Not because you're now superior to anyone. That's not interesting. But because the thing has become alive in your hands. For me, one of the great pleasures in science is precisely that moment when a mystery that was foggy becomes clear enough to play with. Not finished. Not ultimate. Not final. Clear enough to play with, because play is a very serious business in physics. When I fool around with an idea, turn it upside down, ask silly questions about it, imagine impossible cases, compare it with some ordinary object, a wagon, a ball, a glass of water, a spinning plate, that's not wasting time. That is often the quickest route to the heart of the matter. You learn by trying things in your head and on paper. You learn by checking whether the explanation survives contact with reality. You learn by refusing to be hypnotized by your own vocabulary. That last one is important. The human mind is very easily tricked by words. If a word is familiar, we begin to feel that the idea is familiar. But the word is only a handle. The understanding is the thing it's attached to. And sometimes, if you tug on the handle, you discover it isn't attached to anything at all. That's a little embarrassing. But it's also very funny. And in science, if you can laugh when your own nonsense gets exposed, you're going to do much better. Now, why does explaining to another person work so well? Because teaching is a kind of experiment. When I explain something to myself silently, I can glide over the bad parts. The mind is very accommodating. It says, "Oh yes, yes, I know what I mean," and rushes onward. But when I explain aloud, or write it down in plain language, the sloppiness becomes visible. If I say, the particle just wants to go to lower energy, that's suspicious already. Wants? Since when do particles have ambitions? Now, sometimes the kind of phrase is harmless shorthand among physicists. We all know what's meant. But if I'm trying to learn, shorthand can be dangerous. It lets me skip the mechanism. So I ask, what really happens? What states are available? What changes are allowed? What interaction causes the transition? What quantity is minimized or conserved? Now the explanation sharpens. This is why I like to explain to an imaginary student. The imaginary student is a wonderful fellow. He is patient, but he is merciless. He says, "I don't understand that sentence." He says, "Why does that follow?" He says, "Can you give me an example?" And if I can't answer him, then I've caught myself cheating. That's very useful. Picture a freshman sitting in the back row. Bright kid. Honest kid. Not yet trained to pretend he understands. I say, momentum is conserved. He raises his hand. What do you mean by momentum? I tell him, mass times velocity. He asks, why is that the useful quantity? Aha! Now I have to talk about collisions. I have to talk about symmetry. I have to show that in interactions, this combination behaves in a special stable way. I have to connect the equation to carts on a track, billiard balls, recoil, rockets. Now momentum is no longer just a word. It has become a pattern in the world. And that transformation, from word to pattern, is what learning is. If I cannot make that transformation, I have not really learned the thing. Now let's come to the word faster. Everybody wants to learn faster. Fine. But faster than what? Usually, what people mean is this: how can I reduce the wasted motion? That's a sensible question. Here's the answer: you learn faster by increasing the honesty of the feedback. If I spend 3 hours rereading a chapter 1/2 understand, I may feel industrious, but I have poor feedback. The chapter looks more familiar each time, so I feel smarter, but familiarity is not the same as understanding. If instead I spend 1 hour trying to explain the chapter from memory on a blank sheet of paper, I get superb feedback. The blank paper is ruthless. It doesn't care what looked familiar 5 minutes ago. It asks only, what can you actually produce? That is why recall beats recognition. Recognition says, ah yes, I've seen this before. Recall says, all right then, produce it. Only one of those resembles what you'll need when you solve a new problem. So if I wanted to learn faster, I would do less ceremonial studying and more active reconstruction. I would close the book sooner. That sounds backward, but it isn't. I'd read enough to get the ingredients, then shut the thing and try to rebuild the meal. If I can't, I know what ingredient I'm missing. Then I go back and fetch it. That loop is tremendous, and another thing, would always connect the idea to at least one real phenomenon. If I learn resonance, I think of pushing a child on a swing. If I learn electric current, I think of charge moving under a potential difference in an actual circuit, with resistance heating the wire. If I learn angular momentum, I think of a spinning wheel resisting reorientation, or a skater changing spin by moving the arms. A physical anchor helps prevent symbols from floating away. Without that anchor, the subject can become a kind of formal game detached from experience. Sometimes the formal game is necessary. Mathematics is a beautiful and powerful thing, but for learning, especially at the beginning, I want contact with phenomena. Something I can picture. Something I can test. Something that would happen whether or not I had a textbook to describe it. There's also an emotional side to learning, and it matters more than people admit. If you approach a subject trying always to protect your pride, you'll learn slowly. Because pride hates being corrected. But curiosity doesn't mind. Curiosity says, "That's funny. Why did I get that wrong?" That's a much more productive attitude. I like to keep the problem playful. Not careless, playful. There's a difference. Careless means you don't check. Playful means you poke at the thing from different directions because you want to see what it will do. A child learns that way. A scientist ought to preserve some of that. I've often felt that the pleasure of finding things out depends on being willing to discover that you were mistaken. If I already know what the answer must be, then I'm not investigating, I'm defending a position. But if I genuinely want to know, then every surprise is useful. Even the unpleasant ones. Especially the unpleasant ones. Because they reveal reality pushing back against my imagination. And that's the whole game. The world is what it is. My job is not to force it into my prejudices, but to find out how it works. Learning goes fastest when I keep that spirit. Not, how can I look smart quickly? But, what is really going on here? That question has much better fuel in it. So let me boil the whole thing down. If I want to learn something fast, I do not ask, how can I memorize this efficiently? I ask, can I explain this simply, clearly, and correctly? If I can't, then I have located the work. I take one idea at a time. I explain it in ordinary language. I turn the symbols back into pictures and consequences. I test it with simple cases, extreme cases, and real cases. I look for the exact place where my explanation breaks. Then I go back, repair that piece, and try again. And I keep going until the idea becomes something I can handle, not just something I can repeat. That is the whole trick. It's really a method for not fooling yourself. And that is why it works. Because the fastest learning is not the learning that makes you feel knowledgeable soonest. It's the learning that removes false understanding soonest. There is a tremendous delight in getting hold of an idea so well that it becomes transparent, so that instead of staring at the words, you can see through them to the phenomenon underneath. At that point, the subject is no longer a school subject. It becomes part of nature again. It becomes motion, light, force, probability, structure, something out there in the world, doing what it does whether or not you are clever enough to describe it. And then learning stops feeling like storage. It starts feeling like discovery. So the next time you study something difficult, try this. Close the book. Take a blank sheet of paper. Write the idea at the top. And then, as honestly as you can, explain it. If the explanation falls apart, wonderful. Now you know where to begin. That little collapse, that's not failure. That's the door opening. And if you can learn to enjoy that moment, then you can learn almost anything, because now you're working with reality, and reality is the best teacher there is.